Chapter 11 is going to cover equilibrium and elasticity, which should be of particular interest to engineering-minded folks. What we're going to do is we're going to talk about what conditions need to be met for a body in equilibrium. I'll mention very briefly the center of gravity and how it relates to stability. Very important, we'll be looking at solving rigid body problems in equilibrium, and then we'll change gears a little bit and talk about extending Hooke's law to rigid bodies. So we'll talk about tension, compression, and pressure, and see what happens when a body is stretched past its breaking point. How does equilibrium relate to real life? Well, any object that we build, bridges, buildings, aqueducts, so on and so forth, they're designed so they do not accelerate. They are what we call in equilibrium. So being able to solve equilibrium problems is of particular interest to engineers, mechanical engineers specifically. Although it does actually turn out that what we think is rigid really isn't entirely rigid. Things are going to deform if you put enough weight on them. So we're also going to introduce concepts of stress and strain and look at how real bodies actually do. On the last slide I said that the condition for equilibrium is that an object is not accelerating. So from that I can come up with two conditions that would say an object is not accelerating. The first condition is that there is going to be zero net force on an object. If there is zero net force, then it will not be accelerating. The acceleration must be equal to zero. The second condition is going to use the concept from Chapter 10, the concept of torques. An object will not be accelerating if all of the torques are equal to zero. So there can't be any linear acceleration and there cannot be any angular acceleration. So these are the two conditions for equilibrium. So very important slide, by the way. Let's take a look at figure A. This body is going to be in static equilibrium. If I look at all the forces on this, there's no forces in the x or z, and in the y direction I'm going to have 2f in the positive y direction. I'm going to have 2f in the negative y direction. Therefore the sum of forces in the y direction is going to be zero, so it meets all of these criteria. If I look at the torques, this force is going to apply a torque, which is going to be that force multiplied by that distance L, and it's going to be a negative torque. It's going to be in the clockwise direction. This force is going to produce a torque of equal magnitude, F multiplied by L. However, it's in the positive direction, so those torques are going to sum up to be zero. So we do meet this criteria as well. Therefore, this body is in static equilibrium. Forgot to mention, but this force acts at the point of rotation, so it causes no torque at all. If I look at figure B, here I meet all of the force criteria. I'm going to have zero net force. I have a positive force and a negative force. However, if I look at the torque criteria, I'm going to get a negative torque. That's going to be negative force multiplied by that length L. This one is also going to give me a clockwise torque, negative force multiplied by L. So my sum of torques is not equal to zero. Therefore, this object is not in equilibrium. You can kind of look at C here and say, okay, for this one, the sum of the forces in the y direction is not going to be equal to zero, so this object is also not in equilibrium. However, this particular one, if you summed up all the torques, here I have a force at some distance L, that's going to give me a torque of negative force multiplied by length. This one is going to give me an equally opposing torque in the opposite direction, so I can have zero net torque, but I didn't satisfy the force criterion. I just want to mention very briefly this concept of center of gravity. We can essentially treat very large bodies as if their weight is going to be condensed down to a single point. That's going to be the center of gravity. For all of the cases that we're going to look at here, the center of gravity is essentially the center of mass of a body. So we can pretend that all of the weight is going to be at the center of mass, which is also called the center of gravity. It turns out that if you build a very, very, very large object and gravity varies along the length of the body, then the center of gravity is not quite going to be the same as the center of mass, but for everything we're going to deal with, we can treat the center of gravity as the center of mass. So let's take a look at solving equilibrium problems. For example, suppose we have a car, and you know that a car is going to have more weight up front than in the back because you have the big heavy engine pulling down on it. And suppose you wanted to do some crazy Dukes of Hazzard style stuff and get your car airborne. You want to figure out where the center of gravity is. That's going to be the point at which your car is going to rotate about. So could be a good thing to know. So you take your car and you put a scale right here under the rear wheels, a scale under the front wheels, and you find out that 53% of the weight is on the front wheels and 47% of the weight is on the rear wheels, and you have your weight going downwards here. You know that your car is in equilibrium. The sum of the forces in the y direction are indeed equal to 0. We have 0.47 of the weight going upwards. We have 0.53 of the weight going upwards, and then we have the weight of the car going downwards here, so it does indeed meet that criterion for equilibrium. You also know that it is not rotating, so it is in equilibrium. We can now use that to find the center of mass. What we can do is we can say, I want to calculate the sum of the torques here. Equilibrium tells me that these must be equal to 0. I can calculate them about whichever point I want. Here I'm just going to pick the rear wheels. So the sum of the torques is going to be the forces multiplied by the distance. So you're going to get a torque from the weight and then a torque from the front wheels, as well as the torque from the rear wheels. So here we're going to have the weight acting at that distance to the center of mass, or the center of gravity. And then you're going to have the force, the weight of the car from the front wheel, 0.53 multiplied by the weight, and that's going to be at 2.46 meters. So that's a multiply right there. And we could also add on the force of the rear wheels, 0.47. The distance to the pivot point, however, is going to be 0. So that term's going to go away. So the first two terms are going to sum up to be 0. We can go ahead and calculate that out, and the distance to the center of gravity is going to work out to be 1.3 meters. Example 11.13 here is a very good problem to make sure that you understand what is going on here. So not only will I 1-star this, I'll 2-star it, and I'll even 3-star this particular slide. Make sure that you're comfortable with following this example, and even do try to solve it on your own without necessarily looking at what I'm going to write down or what the book writes down. So here we have Sir Lancelot on a ladder up against a frictionless wall. First thing we have to do, and what we want to do, is we want to find out the normal force and the frictional forces are. To do this, the first thing we have to do is identify all the forces that are occurring here. We are going to have his weight going downwards. We have some weight of the ladder also going downwards. It's going to have a supporting force going upwards from the ground. There's also going to be a frictional force right there. And there's also going to be a normal force right over here from this wall. Normal forces are always perpendicular to the surface, if you remember correctly. And we also know the angle here. So the book's gone ahead and it's drawn a free body diagram much prettier than what I could possibly do here. And it's also gone ahead and calculated out what these lever arms are going to be when we start looking at torques. So make sure that you're comfortable calculating those lever arms. What we're going to do in this type of problem is we're going to say it is in equilibrium. So I've got some criterions that I can say. I can say some of the forces in the x direction are going to be equal to 0. So here I'm going to have a frictional force in the positive x direction, and then a normal force 1 in the negative x direction. So if I can figure out what my normal force 1 is, then I know what my frictional force is. These forces will be essentially equal. I can then write my other criterion. Sum of forces in the y direction now must be equal to 0. And here I'm going to have the normal force 2 in the positive y direction. And then I'm going to have the first weight, which is going to be 800 newtons downwards, and then the weight of the ladder also downwards, 180 newtons. So now I know what one of my normal forces is. That's going to be 980 newtons. Now to solve for the normal force 1, I need another set of equations. What I can do is I can say I know that this guy is in equilibrium, so I'm going to say the sum of the torques are going to be equal to 0. And I can choose my pivot point wherever I want it to be. The best point to choose it at is going to be point B right there, because I'm going to take it about the bottom of the ladder. The reason I choose the bottom of the ladder is because I don't know what that frictional force is. So I can choose my pivot point such that that frictional force is going to act with a lever arm of 0, and it will essentially produce no torque. I could have also chosen it to be up here. I don't know what that guy is either. However, the reason I chose it to be at point B is because this makes N2 also at the lever arm of 0, and that's one less term I have to write and worry about. So the sum of the torques now is going to be the forces multiplied by their lever arm. So I'm going to have 800 newtons with a lever arm of 1 meter, and that is going to produce a clockwise torque. Clockwise torques are going to be negative. The same with the weight of the ladder. It's going to be 180 newtons multiplied by 1.5 for the lever arm, also negative. And then I'm going to produce a positive torque with the normal force 1, and that guy is going to act with a lever arm of 4 meters. So normal force 1 multiplied by 4 meters. This equation right here allows me to solve for normal force 1. I'm going to solve that guy out. It's going to be some number, and then I can use that with my sum of forces in the x direction to come up with the frictional force. So this is indeed an excellent problem to look at all three conditions for equilibrium and use them to solve a problem. Same type of thing if you want another problem for practice to work on getting familiar drawing the free body diagrams and so on and so forth is 11.4. Same type of thing, we're going to say sum of forces in the y direction must be equal to 0. Sum of forces in the x direction must be equal to 0. And lastly, sum of torques are going to be equal to 0. And now I can solve for tensional forces as well as the forces that are on the elbow. Turns out in the real world, objects can be in equilibrium. They can meet all the criterion that we have talked about now, but they can be deforming a little bit. Think about if you're on a swinging bridge and you're jumping up and down, having a grand old time, the bridge is going to be deforming. So we're going to talk about some of the physics behind this. In the simplest possible case, we can think about a spring. Right? We apply a force, it's going to deform the spring, and we know that how much force you apply is going to be related to kind of how stretchy it is, the spring constant, and then you get a deformation. If we talk about real objects now, and not just springs, it turns out real objects actually have some size associated with them. So we're going to define the stress as the force per unit area, and we're going to talk about the strain as the fractional deformation of the body due to the stress that you put on it. And the elastic modulus is simply going to be the stress divided by the strain, kind of how stretchy a real object is. So we could also write stress is going to be equal to some elastic modulus. I'm going to just call that a constant, call that y, multiplied by the strain on a body. And you can kind of see stress is going to be related to force per unit area, and the strain is going to be related to the deformation of the body. So Hooke's law here kind of is a boiled down version of this equation right here relating stress and strain. I can actually talk about two types of stress and strain, tensile and compressive. One of these, the forces are going to be stretching an object out, pulling on it. One of them, they're going to be compressing an object. So we can define tensile stress here to be the force divided by the unit area, and the tensile strain to be the deformation of the object relative to its initial length. So what we can do is we can say, okay, suppose we have an object, it's a real object, it's got some size associated with it, it's got some area, it's got some initial length, and I'm going to take two forces and I'm going to pull on this object. Because I'm pulling on this object, I'm applying some force per unit area, and I have stretched that object out by this length delta L. This elastic modulus, how stretchy the object is going to have a specific name called Young's modulus, and again, that's simply going to be tensile stress divided by tensile strain. So this is kind of the spring constant for a real body. Same type of thing applies for compressing an object. If I have an object of a certain area and I apply two forces inward to that object, you can kind of think of a bridge or something like that for this type of case, then I'm going to essentially try to shorten the length of that guy, and I can say the same thing. I can calculate compressive stress, I can calculate the compressive strain, and I'm also going to have a Young's modulus for compressive forces, which is simply going to be the stress divided by the strain as well. It turns out this creature called Young's modulus, or essentially how stretchy an object is, has been measured for many objects. We can take a look at this table right here and see that lead is not going to stretch very much compared to, say, something like steel. We can also define the bulk modulus and shear modulus, which I'll talk about in the next couple of slides. One thing I forgot to mention in the last one were the units here. An object is going to have stress, which is going to be the force per unit area, stress is going to have a unit of newtons per meter squared, and which can also be written as a Pascal, which is a unit of pressure, newtons per meter squared. The strain is going to be the change in length divided by the original length, so it would be in meters divided by meters. So the strain is going to be unitless, and the ratio of these two, the Young's modulus, is therefore going to have units of newtons per meter squared or pascals. Real objects can actually be undergoing tensile and compressive strength at the same time. If I have a beam and I put a force down on it, you can kind of picture all these particles right here are getting pushed together. The top of the beam is undergoing compression. All the particles at the bottom part of the beam are going to be pulled apart, so the bottom of the beam is actually under tension. And this center line of the beam, that guy right there is actually going to be not undergoing tension nor compression. If you think about why an I-beam is shaped the way that it is, it could just be a regular old beam like that, but since the middle is not undergoing compression, it's not undergoing tension, we just don't need all that material there. It's a waste of material to have that there. It's extra weight and it's extra resources, so an I-beam doesn't need to have much mass there near the center. Just a very quick definition here. We can talk about this happening in 2 dimensions. We can have the force on all sides of an object. It's going to give us pressure, and that's going to therefore not change, it's going to change the length in the x, it's going to change the length in the y, it's going to change the volume of an object. So we can define this bulk modulus the same type of way, where it's going to be a stress divided by a strain, only now it's been extended to 2 dimensions. I'm really not going to do a whole lot with this. Shear stress is fairly similar. Rather than having our forces be perpendicular to the surface, now I'm going to have my forces acting parallel to the surface, and as you would expect, that's going to deform the object kind of like this. Same type of thing, we're going to have a shear modulus, which is going to be a stress divided by a strain. And one thing to kind of note, if you go back and you look at table 11.1, all of the values for shear modulus are much larger than, or much smaller than for Young's modulus. It turns out that it's actually much easier to stretch an object by applying these forces in a shear sense than trying to compress an object or to pull an object apart. The last thing I want to talk about is this concept of elasticity. It turns out that when we stretch an object, it will return to its original shape as long as you don't stretch it too far. If you ever played with a slinky when you were a kid, you certainly know if you stretch a slinky too far, it never goes back to the original shape. So as long as you don't apply too much stress to an object, it's in what we're going to call this elastic limit, where if you stretch it, it will come back into its original shape. If you apply too much force and you stretch it too far, it's going to go into this plastic region where essentially it will never return to its original shape. So if you apply too much stress and you stretch it too far, then the shape will never be the same again. And if you keep on applying more and more stress, more force, at some point the material will fracture. So that would be called the breaking point, or the breaking stress. And we can take a look at what these are for various materials, and for people that are going into engineering, these are things that you have to worry about. You don't want to have an object under so much stress that it's going to break. So the table here shows breaking stresses. Now, typically you don't know what the change in length of an object's going to be, but you know the forces that are involved. You're going to know the area of the material, and you're going to know what the material is, so you're more than likely going to know Young's modulus. So you can use what we know about stress, strain, and Young's modulus to calculate how much stress an object is and make sure that you're well below the breaking stress of an object.